This video is about the simple pendulum. We'll start by examining the forces that act on a simple pendulum, and then we'll learn about its period. We'll begin with the forces. Let's start by stating that a pendulum oscillates with simple harmonic motion when the amplitude of the oscillations is small. This means that the displacement angle of the pendulum should be less than 15 degrees. We'll examine the forces that act on the pendulum bob as it is passing through the equilibrium position, when it is halfway between the equilibrium position and the maximum displacement position, and finally when it is at the maximum displacement position. You have probably noticed that the displacement angle in the last diagram is more than 15 degrees. I created the diagram this way so that it is easier to see the forces when we draw them. Also, I have not included diagrams for when the pendulum is swinging to the left. The reason is that the forces acting on the pendulum when it's swinging to the left are practically the same as when it is swinging to the right. Of course, the direction of the forces will be different, but their magnitude and origin are exactly the same. And the final note, that we are omitting air resistance and any kind of friction. So let's see the forces that act on the pendulum bob as it's passing through the equilibrium position. Of course, the gravitational force is always present and is pointing downwards. Let's label this force as mg. The other force that acts on the bob is the tension in the string. In this position, it is pointing vertically upwards. The question is whether it's larger or smaller than, or maybe equal to the gravitational force. As the pendulum bob is passing through the equilibrium position, it is moving on a circular path. When an object is moving on a circular path, there must be a centripetal force. Since here the centripetal force is the vector sum of the tension and the gravitational force, moreover the centripetal force must be pointing towards the center of the circular path, therefore vertically upwards, the tension is larger than the gravitational force and looks like this. Let's move on to the next diagram. We still have the gravitational force pointing downwards. Of course, its magnitude is the same as before, and we have the tension pointing along the string. Since here the two forces are neither on the same line nor perpendicular, we'll resolve the gravitational force into components. One component will be parallel to t and the other perpendicular to it. To be able to express these forces better, let's name the displacement angle of the pendulum theta. So the component of mg that is parallel to t is mg cosine theta, and its component that is perpendicular to t is mg sine theta. Based on what we learned about simple harmonic motion earlier, we know that the velocity of the pendulum bob here is less than the velocity at the equilibrium position. This means that a centripetal force is still present, therefore the tension is larger than mg cosine theta. So what about mg sine theta? We also learned earlier that in simple harmonic motion, a restoring force acts on the object. For our example here, it is mg sine theta that provides this restoring force. Recall that the magnitude of the restoring force is proportional to the displacement from the equilibrium position. Going back to the first diagram for a moment, we can see that here the displacement is 0, which means that the restoring force is also 0, which is also confirmed by the fact that here only vertical forces act on the pendulum bob. By now, you can probably guess how the forces will look like on the final diagram. Let's go ahead and draw these together. We have the gravitational force, which we can resolve into two components based on the displacement angle. Once again, we get mg cosine theta and mg sine theta. So how does the tension look like here? Recall from earlier that at the maximum displacement position during simple harmonic motion, the object stops for a moment so its velocity is 0. This means that the pendulum bob at this moment is not moving in a circle, therefore the centripetal force is equal to 0, so the magnitude of the tension is the same as the magnitude of mg cosine theta. As before, mg sine theta provides the restoring force, which is larger than in the previous position. This also makes sense based on what we learned earlier about simple harmonic motion, because the restoring force is at its maximum at the maximum displacement position. A final point to add here is that the direction of the restoring force at any point is tangent to the circle. Or, put differently, it is perpendicular to the tension. Now that we understand the forces that act on a simple pendulum, we are ready to derive the equation for the time period of the pendulum. Let's start with the force diagram for the pendulum when it is displaced from the equilibrium position. As we saw earlier, the restoring force is equal to mg sine theta. We can write that this is equal to m times a, where a is the acceleration due to the restoring force. For small angles, sine theta is equal to theta. This is based on a concept called small angle approximation, which I won't explain in detail here, but that we can use since the angle for a simple pendulum in simple harmonic motion is less than 15 degrees. So our equation changes into mg theta is equal to ma. Let's go back to the diagram and draw a sector. The radius is equal to the length of the pendulum, so I will denote it with L, and the arc length is equal to the displacement of the pendulum bob, so I will denote it as x. You might have already learned the arc length formula in math. According to this formula, the arc length is equal to the radius multiplied by the angle at the center, when the angle is in radians. So for the diagram here, we get that x is equal to theta multiplied by L. Expressing theta gives us that theta is equal to x divided by L. Substituting this into our equation, we get that m times g times negative x over L is equal to m times a. I am using negative x in the equation because I want to show that the direction of the displacement, so x, is opposite to the direction of the acceleration, so a. We can cancel m and slightly rearrange the equation to give us a is equal to negative g over L multiplied by x. We learned earlier that a is equal to negative omega squared times x. Omega in this equation is angular frequency. Comparing this equation with the one above, we can see that g over L is equal to omega squared. When we take the square root, we end up with omega is equal to g over L under the square root. Recall from earlier that omega is equal to 2 pi over t. T is the time period of the oscillations. Combining this equation with the previous one, we can equate square root of g over L to 2 pi over t, and after rearranging, we get that t is equal to 2 pi divided by g over L under the square root. When we divide by a fraction, we can multiply by its reciprocal, which gives us the formula for the time period of a pendulum that we find in the IB Physics data booklet. Here are the variables that are present in this formula. I did not include pi in this table, but you already know from math that its value is approximately 3.14. If the steps of how we got to this formula are not fully clear, don't worry too much. The derivation itself is not part of the IB Physics syllabus. You just need to know what the variables mean and be able to apply the formula on problems that involve a simple pendulum. Let's summarize what we have learned in this video. We started by analyzing the forces that act on a simple pendulum as it passes through the equilibrium position, the point that is halfway between the equilibrium position and the maximum displacement position, and as the pendulum bob stops for a moment at the maximum displacement position. We discovered that the restoring force is equal to mg sine theta, as shown on the diagrams, and that the direction of this force is tangential to the circular path that is followed by the pendulum bob. Then we derived the pendulum time period formula, and we listed the variables that are present in this formula. A final reminder here that on your IB Physics exam, you only need to know how to apply this formula, but you don't have to know how it is derived. This completes our discussion about the simple pendulum.